the YouTube channel. Hello and welcome back to Organic Chemistry 2342 summer session. Okay, I'm going to continue on with chapter 12, our section 4, alcohols from carbonyl compounds. And so I'm going to start sharing my screen. And let's see if the internet behaves today. Hey. It looks like it is. All right. So this is going to be section 4. This will be a separate video on YouTube as well. It'll be up today. I had some glitching issues this morning, so I want to re-record it. But after that, 12, 3 and 4 will be up today, as well as 13, 1 and 2 will be up today. So we'll have all those available to us. Okay, so now we're going to continue on with those organometallic reagents. We learned that we can make alcohols, both all primary, secondary, or tertiary alcohols based on what we started with, okay? We can make primary alcohols from formaldehyde and formaldehyde only, secondary alcohols from all the other aldehydes, and ketones, esters, and acid chlorides will give us our tertiary alcohols, okay? So now that we know that we can make these alcohols from these different organometallic reagents, let's figure out how to figure out what reagents we had to use to make the product we have, okay? And so when we do this, we call it retrosynthetic analysis, okay? So if you want to make something and you want to figure out what to start with, this is what we call retrosynthetic analysis, okay? And so I'm going to show you how to attack any organic compound to make it so that you'll know how to make that compound through this Grignard reaction with an aldehyde or a ketone, depending on which one you have. So the general concept is when we have a product of when we have something we want to make, okay, we need to figure out what to start with to make it, okay? So if we have our tertiary alcohol, and let's just say we have 3 different groups here, right here, we need to figure out where to start, okay? And we know we want to start with an organometallic reagent, and so we think that we want to start with some kind of aldehyde or ketone to get to our product. And so the idea is, what do we do to back up and say, oh, I had to start with this compound here plus our other compound as our organometallic here, okay? So what we're looking for is where to find the different reagents we'll need to use, okay? And I'm going to use an example here of 3-pentanol, okay? So let's go ahead and draw 3-pentanol here. 1, 2, 3, 4, 5, and OH right here, okay? Now that means that there's a hydrogen here, okay? So first off, we're looking at this and saying, oh, we have a secondary alcohol, okay? If we have a secondary alcohol, that means we started with an aldehyde, okay? So we need to go through a stepwise process and figure out where to do this, okay? So let's think about this. If we had an alcohol, we have this alcohol and we want to break it apart, we can break it apart in one of 2 ways, okay? So let's draw the compound again here. I'm going to leave that hydrogen off just because we know it's there. And I'm going to say, well, we can break it here or we can break it here because we have to have that carbonyl where the alcohol was. So we know that the carbonyl has to be on one of those 2 components, right? So if we're breaking it at one of those 2 components, let's just break it there instead, okay? That means we had a carbonyl on this side with 2 carbons and a hydrogen, and we had something on this side with 2 carbons and some kind of metal group attached to it, okay? So let's be sure that this actually worked right here. So let's take our proposed starting material here of our propanal, right here, it's propyl aldehyde, propanal, right here. And let's say we have to have 2 carbons on here. Let's use an ethyl Grignard CH2CH3 with, let's use lithium, ethyl lithium here. So if we're using ethyl lithium as our nucleophile right here, when we do that reaction, we would have these electrons come over here and attack the carbonyl and generate a new carbon-carbon bond. So that ethyl group would be on this side, right here. And that oxygen is going to have a negative charge on it right when we hit it, and then have that, and then we have that other hydrogen there. So this half of the component is written on this side, and this half of the component came from the nucleophile. And then, of course, the final step for the synthesis is going to be to protonate down alcohol with water to give us our final product. Okay. So the concept here in the retrosynthesis is that we want to be able to break apart the compound knowing exactly where your carbonyl compound was. Okay. So let's try another one of those real quick, and to make it different, we're going to start with a different compound right here. We're actually going to end up making let's do methyl ethyl cyclopropyl alcohol. Okay, so let's do this right here. And so there's a couple different ways we can break this apart, right? So I'm going to draw it differently. I'm going to draw it such that we have the methyl group up here, the ethyl group over here, and the skirt down here. I mean, sorry, the cyclopropane down here. So we have a couple different options for how to break this apart. We can break it apart here. And so we will be attacking with some kind of ethyl lithium reagent right here. Okay. If we attacked it here, we would be attacking it with a methyl lithium reagent right here. And if we broke it apart here, we would be attacking it with a probably a Grignard or some other cyclopropyl group here. Okay. So what we have to do is now pick one and say, okay, let's pick this one right here. Now we have to figure out what the carbonyl compound was. And since we're adding this, we're breaking this bond, that means that this methyl group and this ethyl group were already on the carbonyl when we started. If we have two R groups on that carbonyl, that makes it a ketone, which means our starting carbonyl compound must be the methyl ethyl, or in this case, butanone. And we attacked it with some kind of cyclopentyl organometallic compound to make this system here. Okay, so by looking at your product and knowing you're attacking it with an alkyl metal reagent, you can figure out what is your starting materials. Okay, so that's the whole concept of the retrosynthetic analysis. Okay, so what you'll see is that as you go through the book and the problems in the book there, this will come up time and time again. How do I make this? What were my starting materials? And this is kind of an approach on how to do that with these organometallic reagents. Okay. So I said before that because these organometallic reagents are very basic and are very strong nucleophiles, there's a lot of restrictions with the substrates you can use, the things you can react it with, or even the solvents you can have these reactions in, okay? So for example, you can't have anything with an alcohol or an amine because these are hydrogens that can be abstracted by that base, okay? And that goes for secondary amines or primary amines. As long as there's an acidic hydrogen on there, you can't do it. Carboxylic acids have that acidic hydrogen on them. You can't do anything like a sulfonate right here, a thiol, anything with an acetylene on it, because that hydrogen is pulled off by those organometallic reagents right here. And there also can't be any other group you don't want to react. You can't have any other ketones. You can't have any other aldehydes. You can't have any other esters or amides. And also, it turns out that you can't have nitro groups, because those will, the nucleophile will actually attack the nitrogen of the nitro group. You can't have cyano groups, the CN, C triple bond N group, because it's going to react like a carbonyl too. And of course, you can't have any epoxies on any of your groups. This goes for not only the substrate you're working with or the chemical you're reacting on specifically with your organometallic reagent. You can't have any of these things in the solvent you're using for the reaction. So you can't use acetone as a solvent because it would react with your organometallic reagent. Okay. So, and the first thing that we have to think about is because anything with an acidic hydrogen, we have that acid-base reaction happening, okay? So, and then anything that's a carbonyl or carbonyl adjacent material will react with these things. And so if we had a compound that looked something like this right here, and we wanted to react that with let's just do a methyl Grignard. Okay, and you say, oh, well, I want to use this as a nucleophile and I want to attack this carbonyl and make an alcohol, okay? Well, we can't do that because this alcohol here is going to react first. The acid-base reaction happens before the nucleophilic attack on the carbonyl. So what's going to happen is this reaction is not going to go, because what it's going to do is it's going to form the salt. O minus, and then that reaction is done. It's not going to form the product you want to form, and the byproduct is, of course, going to be methane in this case, because it took the hydrogen off here, it added it to that carbon anion, and it goes away. Okay, so if we can't react it with things that are already on there, if we can't make an alcohol out of this carbonyl because of the alcohol here, then that would really limit us to what we could do. So we have a strategy for getting around this, and it's called use of protecting groups, okay? So basically, in this problem, we had an alcohol already on a product that we wanted to create a new alcohol with, but we couldn't use it because that hydrogen on the alcohol would deactivate our organometallic species and not make the reaction work. So instead, what we can do is we can actually remove that hydrogen and protect that oxygen with some other group so that we can then have the reaction with the carbonyl group happen first, okay? And so this is called the protection-deprotection group, and it involves 3 steps for converting your material to the product you want, okay? So the first thing we need to do is convert our alcohol group into something that does not have that hydrogen on it. So we can't convert it to a carbonyl because that would react. So we need to create some other, like an ether or some ether derivative so that it won't react. Then we'll actually attack our carbonyl with our organometallic species, but then we have to remove that protecting group, and that's called deprotection, okay? So one of the common ones we use is what we call the Silyl Ether, okay? And so the general reaction is an alcohol. Actually, let me switch over to black here. If we take OH right here and react it with some kind of organosilicon reagent, we can convert it to an R group with an O, Si, and then some kind of alkyl groups hanging off of that silicon, okay? What this creates is a silyl ether, or an ether from a silicon and an oxygen, and then we have an ether with the oxygen and the carbon, okay? Ethers don't react in these nucleophilic systems, okay, unless they're that 3-membered ring, okay? So we have one that's really common, and it's called the Tert-Butyl dimethyl silyl ether derivative. And so what we can do is we can take our compound, and what that looks like is we have an Si right here with a T-butyl group on it and 2 methyl groups on it, okay? And this is the group that you're going to use to protect your system here, okay? So how does this work, all right? So let's say we want to do that same reaction with that ketone we had before with that alcohol on it, and we couldn't attack it with our alkyl Grignard, okay? Because, or our alkyl metal group, okay? Because it would have reacted with this species here. So what we can do is we can actually protect that right here and turn it into something that will not react with that organo species right here. Then we can actually do that attack with our methyl, and let's use a methyl Grignard. And then that would generate our first step is with the methyl Grignard, second step is with water. Our new, and the protecting group is not changed during the reaction. And then we actually have to remove the protecting group to generate our new desired dialcohol product right here, okay? So what would that look like? What would be used for that, okay? So the most common way to do that is with these silyl ethers. And the way we do that typically is we take some kind of alcohol here and we react it with the chloro derivative of the silicon reagent we're trying to use. And in this case, I'm using chloro T-butyl dimethyl silane. And so I guess, let's see, they call it TBS for short, okay? And when you react that in the presence of a base, this particular base is a heterocycle known as imidazole, right here. This will suck up the acid generated by the protecting group here and generate OSI right here, okay? So this is now our protected alcohol right here. So there's a couple different groups we can use. This one's used because it actually is really stable and hangs on there really well. So you'll see this used a lot in our book, okay? Now, the interesting thing is this is no longer reactive to organometallic reagents. It's really not attacked by acid or base very much. So we can run a whole bunch of different types of reactions using this protecting group. But what's really interesting is that this group right here is very sensitive to fluoride ions. So a lot of times they'll take the tetrabutyl ammonium fluoride. So this is this tetrabutyl salt of nitrogen with a fluoride ion. And the fluoride ion will actually clip the silicon off to generate your alcohol, regenerate your alcohol, plus a fluorine silicon bond on your former protecting group here, okay? So you have to use this fluoride ion, will clip this group off, regenerating your alcohol. So if we were to do that reaction again up here, here, we could protect this with that T-butyl group and react just at the carbonyl compound and then deprotect it to get our final product. Okay, all right, so that concludes chapter 12, part 4. And so that's our organometallics and reactions of alcohols from carbonyl compounds, okay? So what I'll do now is go ahead and open up for questions, if anybody has any questions, and transition over to start chapter 13. So we'll have plenty of time for our mock test and our student activity on Thursday. Okay. All right, chat room seems to be quiet. So if there's no more questions, we have about 30 minutes left, and that'll get us all the way through Chapter 13, Part 1, Conjugated Unsaturated Systems, okay? So the cool thing is that this leads us into some new reactivity we haven't seen before. And so we're gonna start with a little bit of how to name things and what to name things. Yes, the test will be over chapters 12 and 13 on Friday. Okay, that's why I want to make sure we get this covered before Friday happens. Okay. So the idea here is that when you have molecules with multiple double bonds in them, they start to react differently than they did when they had individual double bonds here and there. So what we see is a couple different things happening. First thing is we can get certain reactions happening at more than one site. And because those bonds are adding together, you actually generate color. And so, for example, the red color in tomatoes is this very long, extended double bonds that are in a regular pattern, and this is called lycopene. Okay, so let's talk about why we like these conjugated unsaturated compounds and what they're named. So anything with more than one double bond in it, that includes double or triple bonds, okay, it is called a polyene or multiple enes, okay? So you can have a diene, which was 2, a triene, 3, tetraene, etc., okay? So when we name these polyenes, we again use the longest chain that contains all of the double bonds, and then we change the parent hydrocarbon from the alkane to the ene, but we have to note how many enes we have, okay? So if we have 3 enes in our long chain, we have to call it triene. When we have 2, we have to call it diene, okay? And then, of course, we try to number them such that the lowest number is, of the first double bond gives it our first lowest number, and then we number up from there. And, of course, if you remember, we have the possibility of cis and trans, or E and Z. We'll go over that again in another video, but it's also in chapter 12 of your book, okay? So if we look at some of these possible ones we have, some of the simple ones are like this 1,2-propane diene. And this is a very interesting compound in the fact that it is called an alene, and it has a central carbon that's linear because it has 2 different double bonds attached to the same one, okay? But one of the more common ones we have that we'll be using a lot is this right here, 1,3-butadiene. And then as we extend out the chain, we can get to longer and longer dienes and trienes, okay? So in this case here, we have the 1 is from that carbon, and the 3 is from the second, the beginning of the second double bond. So they have the 1,2-diene. We have a total of 5 carbons, so that gives us pentadiene. And the 3,4 double bond at 3,4 is in the cis configuration, which also would yield us a Z configuration. So it would be that Z3, that 3Z configuration. Now, if you have different double bonds and triple bonds in the same thing, we have to do similar to what we did with the alcohol rule where we had an ene all. You have the ene first and then the ine last, okay? But you still name it for the lowest number for the alkene first, and then the alkyne is wherever it is, it falls in the chain. So we can go, by the way, I have a nomenclature review chart I will be posting this week on my website, on the track site. So just to help you review some of the nomenclature systems we have. If we have dienes in circular rings, we note that by saying the cyclo, however many carbons we have, and then how many alkenes we have. So this would be cyclohexadiene right here. And so go through the names and remember them. But the thing I want to go to now is the idea of the diene, okay? So the diene is the first and simplest of the unsaturated conjugated systems because we can have those 2 double bonds that can feel each other or see each other, okay? We have different types of these dienes. We have what we call isolated dienes, which means that we have at least 1 sp3 carbon in between the dienes. What this means is that they are no longer electrically connected, and I'll show you why, but because we have this sp3 hybridized carbon, we no longer have overlap of the p orbitals of the different alkenes, And so we see different reactivity than if we had them spaced evenly apart with just the one sigma bond between the two different sets of double bonds. When we only have a sigma bond between those pi bonds, that means we can start to get overlap of those pi electrons with each other. And when they overlap, they extend the conjugation, and they add color, and they change reactivity. Okay, so why does that happen? Okay, remember that a pi bond starts with a single sigma bond. A double bond has a sigma bond, which is your sp2 hybridized orbital, but then it has a pi bond made by an unhybridized p orbital. Okay, so we have that unhybridized p orbital right here and right here, and we have one electron in each of those on each of those carbons. And so we have our pi bond is that bond that's above and below our sigma bond, generating that second bond. Okay, so that's the structure of our double bond. Okay, now if we have another double bond here, those are also going to have that same structure with the p orbital giving us our double bond here. But notice in this configuration, we have a partial overlap. These p orbitals are in the same proximity to each other. Okay, now are they sharing 100% of electron density there? No, they're not. But because we have the possibility of sharing a little bit of electron density across this pi bond and now across this pi bond, we get what we see as called delocalizing the electrons. We can actually move electrons from one side of this to the other because they are overlapping their p orbitals. Okay, so when we have double bonds separated by only a sigma bond, that's called conjugation. Okay, and that's because these p orbitals can overlap with each other. When we have 3 or more p orbitals on adjacent atoms, we call that delocalized. Okay, why do I say 3 or more? Because we can have a carbocation or a carbanion on a carbon there, and it will have available p orbitals to share in the system. Okay, so let's dig into that a little bit deeper right here. So this is our simplest conjugated system because we have our regular pi bond that we saw before in our other conjugated system here, but we have a carbocation on the end. And remember, our carbocation is sp2 hybridized with an empty p orbital, giving it that positive charge. Okay, so in that case, that empty p orbital, which has no electrons in it, notice our pi bond has one electron on each of those p orbitals here. These can overlap, meaning that we can move that positive charge across all 3 of those carbons. Okay, because we can spread that positive charge out over not just 1 carbon, but 3 carbons, we get stabilized carbocation from this. Okay, so what we can see is in this situation, we have the ability to get a more stable carbocation because not only is it tertiary right here, but it can spread out across all of these. We get this stabilization, and this is our simplest conjugated system because that empty p orbital allows us to share electrons across all 3 atoms. Okay, so if we look at the resonance structure of that, we can start with the carbocation on just one of the carbons, and just by moving the electrons over, because remember, in resonance structures we only move electrons, no atoms are broken, no bonds are broken, no atoms move. We can take that positive charge and move it from one carbon at the end to the other carbon at the end. Okay, which means if we look at our hybridized system here, we have a partially positive charge on one carbon and a partially positive charge on the other carbon, which leads it to be more stable than a regular carbocation. Okay, so this allylic cation has greater stability than a regular cation because of the delocalization. Okay, just like with carbocations, the more substituted that carbocation is, the more stable it is. That means that when you have a multiple substituted allylic cation, that is going to be more stable. It can have one or more substitutions here. Those are always going to be more stable than our tertiary carbocation. Now, our allylic carbocation, because we're going to have a partially positive charge flipping between two primary carbons, that's a little more stable. Our secondary, tertiary, and our lowest stability carbocation is our bind. So, before we learned that our tertiary carbocation is our most stable carbocation, now because of conjugation, we actually have a more stable carbocation, the allylic cation. Okay, and it has everything to do with sharing that charge through these hybrid resonance structures. Okay, so let's look at another way to do that. Okay, another way to do that would be to think about benzene. If you have 3 double bonds in a ring here, then there's nothing that keeps them from going back and forth, and flipping back and forth. Okay, so that has 3 double bonds in conjugation with each other. Remember, conjugation is a double bond, single bond, double bond. Anytime you can alternate double bond, single bond, double bond, those pi bonds are in conjugation. Okay. So if our allylic was the simplest structure we can do, the next most common here is what we call the butadiene, or the diene over 4 carbons. Okay. And if we draw our resonance structures here, we can get a positive charge on one end and a negative charge on the other here, and it'll go back and forth. Because again, all we're doing is moving electrons. We are not breaking any atom bonds. We're not moving any atoms. Okay. So, what other type of conjugation can we have? Well, we can have that same allylic combination across things other than carbon, as long as there's an available p orbital. Okay. So that means we can stabilize a positive charge if you have no electrons in that p orbital, a negative charge if you have 2 electrons in that p orbital, or a radical if you have 1 electron in that p orbital that's unpaired with any other, or a lone pair. Now, in the case of the lone pair, that would be something like in the structure we have for the acetate ion. The lone pair is actually residing on the oxygen as part of that conjugated system, and can be kicked in and transferred back and forth between those 2 oxygen. So technically, this acetate ion resonance structure is an allylic anion across 3 atoms. Okay, so we have our double bond and we have our electrons in our p that go back and forth, back and forth. Okay. So the third type we can have is what we call an adjacent lone pair, or where we have a positive charge that can be shared on 2 different atoms. Okay, so in this case here, we would have an atom, usually something with a lone pair like oxygen or nitrogen, next to something that has a positive charge. And what it can do is take part of the time, have those electrons be shared between that atom and share that positive charge. This happens a lot in things like these cationic ethers, where we can have a resonance structure to where part of the time the oxygen has a positive charge and part of the time the carbon has a positive charge. But this is also a way to have that adjacent conjugation of systems. Okay. We also see this kind of thing in polar double bonds. Remember, when we talked about the carbonyl carbon, we said that it has, by resonance structure, a partially positive side and a partially negative side. And that was because the 2 different extremes for that resonance would be 100% in the double bond form, or 100% in a charge separated form, where the positive charge is on carbon and the negative charge is on oxygen. Okay, so we can see this kind of resonance stability, resonance delocalization in all types of these double bond systems. Okay. So when we're talking about writing resonance structures for these things to figure out whether or not we can do these systems, we need to follow some simple rules for these resonance structures, okay? First of all, these structures just help us imagine where the actual charges could reside to come up with their hybridization, which is what they really look like, okay? So for example, it's not going to be one or the extreme or the other, it's somewhere in between, okay? So the resonance structures that we draw are fictional, it's only the thing that's in the middle that's real, okay? So the second rule is we only move electrons, not atoms, okay? If you move atoms or break bonds, that is not a resonance structure, okay? And all resonance structures must have the proper Lewis structure, meaning carbon can only have 4 bonds or less, and you have to have the correct number of electrons around something. For example, you cannot have 10 electrons around an atom unless it's sulfur or phosphorus. So you have to have your 8 electrons or less, you have to have 4 bonds to carbon or less, okay? And all resonance structures must have the same number of unpaired electrons, okay? So for example, here at the bottom, you can't just break apart a double bond and turn it into 3 different radicals for this. This is not a true resonance structure. What you would have to do is have the electron come over here and be paired. So this is not a true resonance structure, but drawing it such the radicals here and the double bond here is a true resonance structure because you have the same number of unpaired electrons that you had before. 1 unpaired electron, 1 unpaired electron, okay? So the next rule we have is that all atoms included in the delocalized system must be planar, okay? What we mean by that is, remember when we looked at the first one here, to be delocalized, these pi bonds have to overlap, and they have to overlap by being in the same orientation as each other. So that means that this pi bond has to be in the same orientation of this, and we call that planar because it allows for us to have those systems together. So what that means is that this double bond has to be in the same plane as that double bond to be able to share across them. If they're twisted so that one P is oriented 90 degrees from the other P, then there's no overlap and there's no resonance. The energy of the resonance hybrid is lower than any of the resonance contributors, okay? Which means, for example, if you had charge separation where you had a positive and negative charge, that's one extreme, that takes energy. And then if you move it around so there's a positive and negative charge in the other extreme, that takes energy. So obviously, the thing that's in the middle, the resonance hybrid, will have lower energy than either one of the contributors, okay? And then there's also a possibility, if it's not symmetrical, that one contributor might be better than the other, okay? So for example, if we delocalized a positive charge across this compound here, we could have the carbocation be on a tertiary site or be on a primary site, okay? So these are both resonance contributors, and this is the hybrid resonance structure. However, they are not contributing equally. Resonance contributor here contributes more to the hybrid because it's the more stable of the resonance contributor. Even though our hybrid here is correct, we do know that our B right here site actually contains that positive charge more often, has more positive charge than this side because this is the more stable of the contributors, okay? So that being said, let's see, oh, we're going on time. All right, so let's think about stability of the system here, okay? So when we're talking about our stability in these conjugated systems, the more covalent bonds a structure has, the more stable it is, okay? So in the case of this example here, notice we can move it such that we have that charge separation. We have a charge here and a charge here, and that would also contribute to a charge here and a charge here. However, the fact that we have a total of 5 bonds, including 2 pi bonds and 4 sigma bonds, here we only have a total of, 1, 2, 3, 4, 5, 6, 5 bonds here. Here we only have 4 bonds. Notice we have 3 sigma bonds and 1 pi bond. In this contributor, we have 3 sigma bonds and 1 pi bond, okay? So what that means is that this resonance contributor is more stable because it contains more covalent bonds. This has 2 pi bonds and 3 sigma bonds for a total of 5 bonds. Each of these only has 4. So that's going to lead to the more stable structure, okay? So the other thing here is that we see here also is that charge separation actually decreases stability, okay? Because one side wants to act as positive, one side wants to act as negative, it actually decreases the stability. So having a resonance contributor that has both an anion and a cation in the same molecule is less stable than that doesn't have one. That in this case right here, if we did the resonance structure here, the one where we don't have charge separation is always more stable, okay? And lastly, contributors that have an incomplete octet are especially unstable. So those things that don't have that full 8 electrons are less stable than those that do have the full 8 electrons, okay? The stability can be enhanced if any negative charge is on the most electronegative atom. So if you can put a negative charge on oxygen versus carbon, you will more likely do that because oxygen is more stable. It is the more electronegative atom. So that's why we see our resonance contributors for something like this enolate ion. If we have a negative charge on a carbon and a positive charge on oxygen, well, oxygen's more electronegative. It would rather have the negative charge. And so it's actually more stable for us to move these electrons in, move these electrons up to give an uncharged species, which is more stable than either of the resonance contributors on either side. However, this right here is not as stable because our carbon has an incomplete octet and separated charge, okay? So the most stable of the resonance contributors is going to be this one in the middle. Number 1, it has the most covalent bonds, it has the least charge separation, and it has a complete octet on each of its atoms, okay? So that kind of gives us an introduction into what conjugation is, the relative stability of different conjugated systems, some of the requirements for conjugation. For example, the p orbitals have to be aligned to get to conjugation. Now that we have this as our basic set, tomorrow when we start with 13.2, we can show how the reactivity has changed over the system. Any questions on just the introduction to conjugated unsaturated systems? Okay. All right, so what I'm going to do now is I'm going to stop recording and then we can talk freely.